we're now going to have a go at trying to figure out what the nature of the critical point is. So we're using the same example as we used in the previous video, so I can carry on with that. So just showing you what I've done down the bottom here. I'll explain it in a second, but here's the question here, the same functions I had previously. So I've got my first partials, x and y, just copied over from the previous video. So pop back and have a look at those if you're not sure where this bit came from. Okay, so what we're going to do now is try and work out what the nature of each of the two critical points are. So we've got three choices. We can have a saddle point, which is minimum in one direction and maximum in the other direction. Or we can have a true local maximum, which is a maxima in both directions, or a minimum, which is minima in both directions. Okay, so these are the conditions. So we need to establish firstly that they are critical points, so the first partials are both equal to 0, and then notice that this thing here is the same for each of the three cases. So we've got to do the two straight second partials, multiply them, and then subtract the mixed partials squared. And if it's less than 0, we've got a saddle. If it's greater than 0, we've got a maximum minima, and then we just look at the second partials to see if they're greater or less than 0. So it's kind of analogous to the one variable thing, but this is the thing we're checking now. So I need to work out this piece for each of my points. So the way that I normally do this is just with a table. So here's my 2 points that I want to check, again derived from the previous video. And to work out this, I need the second derivative with regards to second x. So here's my first x1, so I just differentiate that again, which is 20x cubed. And the second yy is this one with y again, so it's going to be 12y squared. And this is the mixed partial, so I've done the dx, I have to do that again with regards to y. There's no y's in this, this is just a constant, so it differentiates to 0. And then this one is going to be that one times that one minus that one squared. So for each of these points, I've got to now fill out the boxes. So x is 1, so that'll be 20. Y is 2, 2 squared is 4, times 12 is 48. 0 is pretty conveniently 0, and then we're going to just be multiplying these two and subtracting that one squared, so that's going to be 960 minus 0, still 960. And here we've got, if I copy that point across correctly, it was negative 1, positive 2, so negative 1 cubed is negative 1 times 20 is negative 20. That's the same as that one. That's still 0. Multiply these together is negative 960 this time. Okay, so I now have the information I need to make a call. So looking at each point, so at 1, 2, the key thing we're checking is greater than 0. So it's either a maximum or a minimum. So we just need to look at one or the other of the straight second partials, and they're both positive. So it's this case here. So that's a minimum. Okay, so just going over that again. The key check item is greater than 0. So it's either a maximum or a minimum. And both of the straight partials, second partials, are positive, so they're greater than 0. So it's the situation here, so it's a minimum. And at the other one, at negative 1, 2, what do we have? Well, we have the key check item is less than 0, so it's this case here. So we have a saddle point. Okay, so for this function we have one minimum and one saddle point. Okay, and I find that doing that table is just a really good way of working out what's going on.